Alright, so in this section we want to do some practicing to calculate the molecular weight or the formula weights of different compounds. So if we have a compound, we can also call this the molecular mass or the molar mass. And what is this one called? Sodium, either hydrogen carbonate or sodium bicarbonate would be the correct nomenclature for this guy. So if we were going to calculate the formula weight for this molecule, we need to add up all of the atomic weights of the components of this molecule. So if we use our periodic table, we'll see that sodium has an atomic mass of 22.99 atomic mass units. Hydrogen is 1.01, carbon is 12.01, and oxygen is 16 atomic mass units. And there's 3 molecules of this, so we have to multiply 16 times 3. And then we take the sum of all these individual masses, and that's going to give us the overall mass of the full compound, which would be 84.01 atomic mass units. It's really impractical, if not impossible, to conduct research at the atomic level. So we have to get it to the scale where we can actually utilize things within the research lab. So atoms, ions, molecules, atomic mass units, these really aren't useful measurement strategies to utilize within a research laboratory because they're just too small of a scale. So in the research lab, we really need to think at larger scales. So we need to think in the types of units that we can actually measure in the lab, like grams, milliliters, and this leads us then to this concept of the mole, and for actually doing experiments in the lab. So it's possible to weigh out 24 grams of aluminum, but it's not possible to weigh out or to measure out 24 atoms of aluminum. So the mole then is very similar to the individual molecule. The names are even similar. Mole is actually included in the molecule name. So you probably understand this concept of a molecule without too much difficulty, thinking of it as being a single unit of a particular substance. But our mole is the big scale, and it is 6.02 times 10 to the 23 units of a substance, essentially. So our mole is going to be analogous to the molecule. And when we see our coefficients in our equations at the macro scale, these are going to be equivalent to the moles of the compound that we would need to mix together to get a reaction to go to completion on the other side. So at the small scale, we could say 2 molecules of hydrogen, 1 molecule of oxygen combined to create 2 molecules of water. We could say at the large scale that we could have 2 moles of H2 come together with 1 mole of oxygen gas that would create 2 moles of water. So we've already talked about our concept of a mole being a number of units. And so our mole is going to be very similar to what we would say if we had a dozen. We know that a dozen donuts would be 12 donuts, or 2 dozen eggs would be 24 eggs. So we have a definition for a dozen, that a dozen means you've got 12 things. So our mole really means that we have 6.02 times 10 to the 23rd things. So a dozen represents a convenient counting strategy for things like eggs or donuts, because it gives us a quantity that is very useful. For chemists, the mole gives us a quantity of different compounds that is also very useful and converts to useful measurements in the lab. So it converts to gram weights that are actually very possible and easy to measure inside the lab. So the mole is the counting strategy, essentially, of chemistry. So a dozen is 12, a pair is 2, a score, do you know how much a score is? A score is 20. How about a gross? 144 of something. It's a dozen dozens, essentially. And a ream? You might get a ream of paper. You would get 500 sheets of paper. And a mole is 6.022 times 10 to the 23rd things. So this number, this constant that we assign to the mole, is given the special name. it's given Avogadro's number, and it's given this designation of N to the subscript large a. And it will always remain this constant. This is a constant. So very similar to the way we would use a dozen, we can use Avogadro's number to represent 1 mole of any substance. So 1 mole of carbon atoms is 6.022 times 10 to the 23rd carbon atoms. Same with a mole of chloride ions or a mole of water molecules or any other substance or thing. So we could even have a mole of cats. That would be a lot of cats. So it's so big because molecules and atoms are so small that we have to deal with numbers this big to actually be able to use them in the lab. So Avogadro's number is a calculated number that makes it work. It's the right ratio number to match all of the different masses of the different atomic elements. So it's the number that makes it work. It was the constant that was derived from all of the mathematical equations for all of the different molecular compounds. So what's the atomic mass of carbon? We know from the periodic table it's 12 atomic mass units. So we can say how many atoms are in 12 grams of carbon. By definition, that has to be 6.022 times 10 to the 23rd atoms of carbon. And this is equivalent then to 1 mole. So what's the molecular mass of water? So let me bring up our periodic table again. So if we're calculating the molecular mass of water, we know the formula for water is H2O. So we're going to need 1 atom of oxygen, which is 16 atomic mass units. And we're going to need 2 atoms of hydrogen, each at 1.01 atomic mass units. And so our total mass for our water molecule is going to be a sum of these amounts, or 18.02 atomic mass units. So we can tell how many molecules then are in 18.02 grams of water. That's going to be Avogadro's amount of water molecules, or 6.022 times 10 to the 23rd molecules of water. And both of these number then, if we have 18.02 grams of water, or we have 6.022 times 10 to the 23rd molecules of water, these are both equivalent to 1 mole. So that's our definition of a mole. It's the formula weight in grams of the compound, and it's also this number of molecules of that substance. So Avogadro's number is the number that makes it work. And it's based on the masses, essentially, of the protons and the neutrons that are present in each of the atoms. Because they're in a constant ratio for all of the different atoms, we can come down to a constant number that correlates with the mass weight in grams. And so it's really remarkable because this allows us to make the conversion from the small scale of individual molecules to a big scale that we can actually utilize in the lab at a very efficient rate. So Avogadro's number then represents a counting or a grouping system, and we relate that then to the concept of the mole and the molar mass. So this is relating our counting or grouping system to the actual mass of the compound that we can measure in gram weight inside the lab. So this is very convenient for real-world laboratory experiments. So you'll see molar mass, also referred to as the formula weight or the molecular weight. So all three of these concepts are the same thing. It's just adding up the sum of the atomic weights of all the components of your molecule. So the molar mass is really helpful because we can utilize it to weigh things out in the lab. So we know at the atomic scale that this would be equivalent to 2 atoms of calcium combined with 1 molecule of oxygen to create 2 formulas of calcium oxide. This is too small. So we can convert this to our mole concept. So this is equivalent to 2 moles of calcium combined with 1 mole of oxygen to create 2 moles of calcium oxide. So this is a big enough scale that we can utilize, but it's inconvenient because we can't weigh moles directly. We need to still convert this to the molar mass so that we can weigh this out in grams. So if we convert 2 moles of calcium into the gram weight, we know that each mole of calcium is going to weigh how much? 40.08 grams is equal to 1 mole times 2, that's going to be 80.16 grams. This is a very useful number. We can actually measure that out inside the laboratory. 1 mole of oxygen, O2, is going to contain 2 oxygen atoms. So if we go over and look at oxygen again, is 16 times 2. The formula weight for oxygen is going to be 32. So 32 grams per mole. So we can substitute in 32 grams here. And then we're going to create 2 moles of calcium oxide. So we need the formula weight for 1 mole first. So we know that that's going to be 40.08 plus 16. So 56.08 times 2 is going to be 112.16 grams for the 2 moles that we have. So this is very convenient because we could weigh any of these guys within the laboratory and actually utilize these quantities. And again, you've got conservation of mass from one side to the other. So if you added up 80.16 plus 32, you would find that that equals 112.16 grams. So even though our molecules are combined in different ways, the mass of all of the stuff on the left side is still equivalent to the stuff that shows up on the right side. So this is a very convenient measuring system. We can do this in the lab. So I think we'll stop this section here and then continue on with some examples in the next section.